Hey everyone, welcome back to another LeetCode problem. Today we're going to be doing problem number 2681, Power of Heroes. And this was a problem that was on last week's biweekly LeetCode contest, and it was worth the most number of points on there, so it was the hardest one on there. So let's take a read. You're given an integer array nums representing the strength of some heroes. The power of a group of heroes is defined as follows, and I'll just make a brief explanation. You're getting every single possible combination in this array, and the power is the biggest element in that squared plus the smallest element. So these are every single combinations in this array of any different array length, and you can't have repeats, so if you have 2, 1, you don't need to have 1, 2. And so the power is the biggest element squared times the smallest element, so here it's 2 squared times 2, because 2 is the only one, and something like here would be 4 squared times 1. And it's asking for the sum of every single power, and because it's very large, you can return it modulo 10 to the 9th plus 7. So this problem is definitely tricky, but the first thing you're going to want to see is when you calculate this power, you need the biggest and smallest element. And so one of the better ways to do this would be to realize that we're going to need to sort the array, because if we don't sort the array for all of these subsequences, it's going to be difficult for us to know what's the biggest and smallest element efficiently, where if we sort the array, then we know that if we're on some element, that the biggest element is the element we're on. So let's see what happens when we sort this array. So let's just use this example. So it's going to be 1, 2, 4. Now, how would we approach doing this problem? Well, we can get all possible subsequences, but the problem is our num's length here is 10 to the 5th, so we can't do some kind of just like backtracking or something, because any solution that's n squared time or something like that would take way too long. And also, by the way, if we just do some kind of brute force where we take every possibility, so that would be n factorial, because for every number we can have it with every other number. So like this would be 3, so this would be 6, and it's going to be around there, around n factorial, I'm pretty sure, time. Because yeah, like for 4 we could have every subsequence of everything less, and so on. And that's also going to be way too slow. So the way we're going to do this problem is we're going to break this down into iterations, and we're going to see what kind of arrays we have at every single, if we just loop through all these numbers, what kind of arrays we have, and we're going to see if we can find a pattern. So when we're at number 1, the array we have is just this. Then we're number 2, the array we have is and by the way, but what I mean by the array we have is we're going to say the array that ends with this number, because we want arrays that end with these numbers so we can quickly, so we know what the max is right away. And if we just loop through this, we can just bucket all these arrays into arrays that end with each one of these numbers. So for 2, every array that ends with 2 will be 1, 2, and also 2. Then for 4, I'm going to have 1, 4, 2, 4, 1, 2, 4, and 4. And so what we can quickly see, you can do this with the next number, like put in a 8 or something and write out these arrays if you still don't see it, but you can see that for every number, the arrays that make up this number are all of the previous arrays. So like here, it's all the previous arrays, which would be this one, with this number at the end, and then you also have one additional array with just this number. So for like this, for number 4, if you take these 3 arrays, and you just add a 4 at the end, so 1, 4, 2, 4, 1, 2, 4, 4. And then if you had another number, it would be all of these arrays with that number at the end, and then you just have the one additional array with this number at the end. So how can we use this to get a solution that is faster than some kind of n factorial or n squared? Well, what we can do is we can figure out So let's take a look for, like, for example, if we have this 4, how would we possibly get all of the powers with all arrays with 4? So what would that be, by the way? So let's take a look. So with this first array, it would be 4 squared. And I'm just going to leave it like this in terms squared. So it's going to be 4 squared times 1 plus 4 squared times 2 plus 4 squared times 1. It's a little bit bigger. Plus 4 squared times 4. And that's because for all of these arrays, it's the biggest element squared times the smallest element. So 4 squared times 1, 4 squared times 2, 4 squared times 1, 4 squared times 4. And so if we have access to all of these remaining numbers, sorry, all of these starting numbers, then we can easily figure out what would be the sum of powers at this index. Because if we have these numbers 1, 2, 1, and this 4, then let's call this 1, 2, 1 previous. So 1, 2, 1 would be previous, which would be 4 here. So it would be 1 plus 2 plus 1. Then our power at n equals n squared times previous plus, and then this would be like this. Because we do have this additional number at the end that we always add. So if previous is these 3 numbers in these 3 arrays, we can add them together. So 1 plus 2 plus 1 would be 4. And then we have a 4 here. So it would actually be, the total here would be 4 squared plus 8. And we can see that if we do add these up right here, that this is 1 plus 2 plus 1 plus 4. So this 4 squared times a bunch of values, when you add it together, you can just do 4 squared times all of these values added together. So we can see that if we have this previous somehow at 4, and this previous is, like I said, the starting element in every single array before we get to 4, so it would be 1, 1, and 2, then we can quickly calculate this. And the same thing for 2, we can go to what's the starting element at every single array before 2? Well, it's just 1. So then the power at 2 would be the same formula. So it would be n squared times previous plus n. So what would that be? That would be 2 squared times previous, which is just 1, plus 2. And you can see that that would be the case here, because this is 2 squared times 1, and this is 2 squared times 2. And then here we have, so let's initialize our previous to 0, because in the beginning we have no previous, and then so here it would be 1 squared times previous plus 1, which would be correct, right? So the power of this array would be 1. And so now all we need to do is we need to figure out how do we update our previous from each iteration. Well, what are we doing? So like I said, what are we going, when we go from here to here, and from here to here, and so on, how are our arrays changing? Well, what we're doing is we are doubling the number of arrays we have, and then we're adding this one right here, right? So here we have one array, we double it, or sorry, we don't, we do double it, because now we have 2 arrays, and then we add this one right here. So it would just be, so the number of total arrays we have are actually 2 times previous plus another one. And you can see the same thing here. So we have this 1, we have this 2, so 3, we double it, right? Now we have 6, and then plus 1. So our and we can also see that for the, like, if we're at 4, these previous numbers are the same as these previous numbers, right? So 1, 1, 2, 1, 1, 2. And so our modification to update the previous at each iteration is going to be 2 times previous plus 1. And that's just going to be like this. We're always doubling the number of arrays we have total, and then we're adding that extra one with whatever n we're at. Because basically whenever we're at an n, we just take every single array that we had, we add that n to the end, that makes a new array. So 1, 4, 1, 2, 4, 2, 4, and then we have this n at the end. So this is how we update the previous. And now we simply can go through every single index. We can do this formula right here. the power of n is n squared times previous plus n. And if you don't understand this, you can try to walk through it one more time, and you can also add another number and see what that would look like. So you can add another number like 6, and you would realize, okay, well, if I have 6, I'm gonna need to take every single one of these arrays, add 6, and then I'm gonna have another 6, and you can write what the previous value is at each step. Okay, so let's code this up. So first, we need to sort the list. Let's bring this up here. But yeah, a quick understanding is if this number was very small, like if this number was only 10 or 20, then you can do some kind of n squared or n factorial solution and it would be totally fine because this number is small. But because it's 10 to the 5th, when you square or do a factorial solution, it's going to be way too big. So we do need some kind of linear or a logarithmic time solution. Okay, so first we do a nums.sort. Then we need a total power. Make that 0. We can make a previous. We started at 0, remember? And now we just loop through every single number. So for nums, res, and then we can look at our formula again. So it's n squared times previous plus n. So n squared times, actually, do you also think that whenever you're doing n squared, I think this is faster in terms of runtime, so you can do this instead. Okay, and then times previous plus n. And now remember we have to update our previous, so our previous is going to be 2 times previous plus n, as we can see from our example. So like, for example, if we started with this, what is our previous going to be in this case? Well, our previous is going to be 2 of these, because we have these 2 arrays, right? So we have both of these, and then we also have this n right here. So that's why when you get to 2, our previous is this, this, and this. And so that's our update case. And I think that's it, and then we just return res here. So let's see how that is. Oh, and by the way, we need to also, so it says the number could be very large, so we need to return at mod 10 to the 9th plus 7. I think in Python, you don't have to worry about integer overflow because they give you a ton of space to store your integer, but you do need to mod it at the end because I think if you return something with too many, that has too much memory, so we can even show you here. Let's see. Oh, so this should just be total power. This is power. This is also should be num. Okay, so this one might work, but when we try to submit, yeah, so it says this huge value is not valid for expected return time integer. You don't have to worry about overflow in Python, but you do still have to mod it down. So then we just have to do mod 10 to the 9th plus 7. Okay. And so the other thing I would recommend for problems like this, it could be quite confusing, so if you still don't understand it, maybe try a couple other arrays and write down what these previous values should be for yourself, and then you can even have a print statement in these to make sure you're on the right track, and so you understand it. And another thing is, if you are finding this algorithm difficult, I would say mark these problems and try to redo them in a week or two, because if you're finding the solution I would say for every problem that you're not finding the solution really straightforward, you're just going to forget how to do it. So it's a good habit to, anything that you struggle understanding the solution, mark it down, save the LeetCode problem, and then try to code it up on your own in a week or two, and then that way you have a full understanding of the solution. So let's do the time and space complexity as well here. So time. Yeah. So we're sorting, which is n log n. And then we're just iterating through this num, so this is linear time. So the sort is going to be the thing that's going to take the longest amount of time. And our space is going to be O of 1 because we didn't declare any other data structure. So that's all for this problem, and I'll see you in the next one.